the miscellaneous Mr. Daycock here, and today I'm going to be teaching you about hyperbolic functions. But before we go into the hyperbolic functions, let's recap our trigonometric functions. We of course have sine of theta, cosine of theta, and tangent of theta. And these are often defined in different ways, but for the purposes here, I'm going to define them like this. I'm going to define tan theta as sine theta over cosine theta, and I'm going to define sine and cosine using our complex exponentials. Because one thing we know is that e to the I theta is identical to cosine theta plus I sine theta. And a derivation of that, something that leads on from that, is that e to the minus I theta is identical to cosine theta subtract I sine theta. And this allows us to produce a definition for cosine theta and sine theta, because if I add these, the cosines will add together and the sines will cancel out. So we'll end up with e to the I theta plus e to the minus I theta is going to be equal to 2 cosine theta. And then of course dividing by 2, I end up with e to the I theta plus e to the minus I theta divided by 2 is cosine theta. Similarly with sine, if I subtract these, the cosines will cancel, but the sines will add. And so we'll end up with e to the I theta subtract e to the minus I theta is going to be equal to 2i, notice there is an I on here, 2i sine theta, and then if we follow from that, we get e to the I theta subtract e to the minus I theta divided by 2i is sine theta. And what we can do is we can take these two statements here as the definitions of sine and cosine. And it leads us to an interesting question. What if we were to write these functions without the imaginary parts? What if we wanted to deal with exactly these definitions, but entirely real in terms of our coefficients? In that case, we would be looking at the function e to the theta plus, and in fact for this we tend not to use theta, we tend to use a, so, and I'll get into y later, e to the a plus e to the minus a over 2, and for this one over here, e to the a minus e to the minus a over 2, and these were what we call our hyperbolic cosine and our hyperbolic sine, written like this. This is defined to be cosine with an h on the end, a. And over here, sine h, a. And these, like I say, are the definitions of our hyperbolic cosine and our hyperbolic sine. And they're often pronounced cosh and shine, respectively. And equally, how are we going to do our hyperbolic tangent? Well, our hyperbolic tangent, written as tan with an h on the end of a, is going to be defined to be sine, hyperbolic sine, over hyperbolic cosine. And these are our hyperbolic functions by definition, or at least the definition we're using currently. Now I will get on to why we have these definitions, why they're useful in the next video, what they mean and how they relate to trigonometric functions and why they're like this. But for now, we're just going to have a practice with them, understanding the definitions of them, etc. So, for example would be, can we work out what shine of 3 would be? Just the number 3. just like you might work out what cosine of 0.5 would be. And the answer is yes, because that's just going to be equal to e to the 3 minus e to the minus 3 all over 2. And you can leave it as an exact value, or you can work out what that's going to be, and that should give you 10.02 to 2 decimal places. It will carry on infinitely beyond that, but to 2 decimal places we get that. And equally we can do a similar thing with all the other functions as well. So we can put cosine of 1. What would that be? Well, it would be e to the 1 minus e to the minus 1 over 2. And you could write that as e minus 1 over e over 2. But however you put it, you're going to end up with about 1.54 to 2 decimal places. Or you can go further and you could ask yourself, well, what if I've got hyperbolic tangent of the natural log of 4, for example? Well, then I can just put that into my definition, or my hyperbolic tangent of A is going to be equal to hyperbolic sine of A over hyperbolic cosine, obviously, cosine of A, but in this case, of course, A is our 4, natural log of 4, and each of those, well, that's going to be e to the natural log of 4 minus e to the minus natural log of 4 all over 2 divided by, and this here is the hyperbolic sine, divided by our hyperbolic cosine, which is going to be e to the natural log of 4 plus e to the minus natural log of 4 all over 2. And cancelling those down, we're going to get 4 minus 1 over 4 over 4 plus 1 over 4, which is going to be equal to 15 quarters over 17 quarters, which is 15 over 17. Now, it's a little bit long-winded. As it turns out, there is a way we can simplify hyperbolic tangent. So hyperbolic tangent of just a function of a letter A, well, it simplifies using our definitions of hyperbolic cosine, hyperbolic sine. It simplifies to e to the A minus e to the minus A all over e to the A plus e to the minus A. And there's another way of writing it. If I multiply top and bottom by e to the A, using equivalent fraction rules, we can write that as e to the 2a minus 1 over e to the 2a plus 1. And that's quite often more useful, particularly in working out something like this with a few less lines. And so this is a valid definition for our hyperbolic tangent. Okay, thank you very much, and I'll see you in the next video.